formation of eddies. So this is all about the Reynolds number. So there is a certain value of Reynolds number, critical Reynolds number, below which the flow is laminar and the flow is said to be turbulent if the Reynolds number exceeds the critical Reynolds number. Secondly, we shall go to the Prandtl number. Prandtl number is defined as PR equal to mu Cp by K is equal to nu by alpha. It is defined as molecular diffusivity of momentum divided by molecular diffusivity of heat energy. It is the relative speed with which heat energy and momentum are propagated through the fluid. So, while discussing the development of velocity and thermal boundary layer over a flat plate, it was found that the relative thickness of velocity and thermal boundary layer depend upon the Prandtl number of the fluid. For gases with PR equal to 1, velocity boundary layer thickness equal to thermal boundary layer thickness, or transport of momentum and energy by diffusion process are comparable or equal. For oils, PR is greater than or equal to 1, momentum diffusion is faster than the energy diffusion process. For liquid metals, PR is less than or equal to 1, energy diffusion process is much greater than the momentum diffusion process. Then third non-dimensional number is Nusselt number. Nusselt number is defined as Nu equal to HL by K. So heat transfer coefficient is expressed in a non-dimensional form as a Nusselt number. Nu equal to HL by K is equal to H delta T divided by K delta T by L, where delta T is the temperature difference between the fluid and the wall surface. Thus, Nusselt number is a ratio of heat transfer by convection to the heat conducted through a layer of thickness L. A large value of Nusselt number indicates increased heat transfer by convection. Nusselt number equal to 1 indicates that there will be no heat transfer by convection. Entire heat transfer takes place by conduction. Then next type of non-dimensional number is Stanton number. Stanton number is equal to H by rho Cp U0 equal to H delta T by rho Cp Um delta T. The numerator indicates the heat transfer to the fluid divided by heat transfer capacity of the fluid. Heat carrying capacity of the fluid, which is on account of its mass and specific capacity. So it is also can be defined as, in this way it can also be while fluid is flowing through over a pipe or a plate, it is nothing, it is a wall heat transfer divided by mass heat flow rate. While discussing the Reynolds analogy, we have discussed that Stanton number relates the heat transfer coefficient with the local drag coefficient. For gases with PR equal to 1, Stanton number is equal to Cx by 2. So if you know the value of drag coefficient, local drag coefficient, then for fluids with PR equal to 1, if you know the Stanton local drag coefficient, we can calculate the value of Stanton number. Thus, by knowing the Stanton number, we can find out the value of H by using the formula for the Stanton number. Stanton number is equal to H by rho Cp U infinity. Then fourth is Eckert number. Eckert number is used in high heat transfer problems. Eckert number is equal to U square by Cp delta T. It is defined as dynamic temperature rise due to fluid motion divided by temperature difference. So Eckert number indicates whether the temperature rise due to heat generation effects in the fluid flow can be neglected in comparison with the temperature difference occurred in the heat transfer analysis. It indicates, Eckert number indicates whether the viscous energy generation rates can be neglected in comparison with the temperature differences. Eckert number is very small, means that the temperature rise due to heat generation can be neglected in comparison with the temperature difference occurring in the heat transfer situations. Then fourth is the last, finally it is the Grashof number. Grashof number comes into picture in natural convection. It plays the same role as the Reynolds number in forced convection. Grashof number decides whether the flow is laminar or turbulent for free convection. Grashof number, you know that in natural convection, the force which causes the motion of the fluid is buoyancy force. The Grashof number is hence defined as the ratio of buoyancy force to the viscous force, analogous to Reynolds number, which is defined as ratio of inertia force to viscous force. There is certain value of critical Reynolds number, critical Grashof number, below which the flow will be laminar and the flow will be turbulent for the value of Grashof number greater than the critical Grashof number. Grashof number is given by beta g rho square beta g delta T L cube by mu square equal to beta g delta T L cube by nu square. These are some of the non-dimensional numbers and their physical significance. Thank you.